Now we're going to use IR to distinguish between these molecules. Let's see what we have here in the first molecule, sp2, carbon sp2. So I should have a carbon-carbon double bond, and this say is about 1650 maybe centimeters -1, around that. But I do have a double bond here as well, so in the next molecule, so that's not going to allow me to distinguish them. And same here, so I have also double bond, but there's something here that is different in this molecule, and is the fact that we have a hydrogen attached to an sp2 carbon, and that will give me an absorption, this one, at about 3100 centimeters -1. That is distinct, and I don't have that in the others. The alkene here is tetra substituted on the right hand side, so tetra substituted alkene. This is also tetra substituted, and this is why we don't have that signal, so that I can distinguish the others. Other than that, these are the main signals that are, most important signals. Other than that, we will have, of course, signals due to carbon sp3 hybridized attached to hydrogen, and these are at about 2800. But these are present here. This is a carbon sp3, and yeah, so that is present in all these molecules as well. Okay, so we said the double bond carbon-carbon is present in the tree. The carbon sp3 hydrogen is also in the three molecules. Now, what's different in the second molecule is that we have the OH. And here we have an important stretch. This is the hydrogen attached to oxygen, and that will be at about 34 to 100 to 3200 or so, and somewhat broad band. So characteristic of the OH. So that way I can distinguish at least the last two. Now, in the last molecule, we have an alkene, an alkyne. So we have alkene and alkyne. So alkene here. But the thing is that this alkene is internal. The alkyne is an internal alkyne. So I don't have the vibration due to this hydrogen, which is at about 3200. So I don't have that. Cannot use that. But I do have the carbon triple bond. That will be somewhat weak, but this vibration, it is in about 22 centimeters -1. So we can see we can distinguish this molecule. So all the three were alkenes, but the first one on the left that had a hydrogen, and so I can see the signal, and on the others. The second molecule had an OH, which was easier to assign, and then I have an alkyne, an internal alkyne in the third molecule. Now, when we have carbonyl compounds, the signal of all these compounds, and you can also have here, we can add carboxylic acids to that, for example. We will always have the carbonyl, so notice that is around 1700. 1720, the ketone, but conjugation always lowers that. Notice again that if you compare the ester with the ketone, the ester is a slightly higher wave number, but again, conjugation brings it down. Now, one important thing to distinguish in the same region, so at about this is ketones and aldehydes, so carbonyl groups, 17 or so, 1700, and a little bit under we have the carbon-carbon double bond that we see here. But notice this bond is not as intense, so the carbonyl is much more intense. This is related to the oscillation due to dipole moment. Remember that here we have this bond is polarized in the direction, so electrons are moved towards the oxygen. And you can also visualize this using resonance. If you have a ketone and you do this, you know that you can do a resonance structure in which you will have a negative oxygen here and formal positive of the carbon. So that changes that vibration, and that makes the band more intense. So the oscillation in the dipole moments. So we expect that that's an important thing to remember, because they show up in the same region. Now, that shape is also very important. We saw before that the carbonyl, say the carbonyl was like that, in compared to the carbon-carbon double bond, so which was less intense but also sharper. And say that was in the 1700 neighborhood, let's say. Anyways, the other factor is shape. So here, this two had different shape, the carbonyl and the carbon-carbon double bond. But now, the broad signal is due, in many cases, to because of oscillations that changes the nature of the bond. So this is typical of alcohols where we have hydrogen bonding interactions, as we see here. Remember the hydrogen bond, this is a dynamic process in the fluid, so the hydrogen bonds form and break, you form new ones. So this is constantly changing this distance and the force constant. So this is why we have an average. This is changing of the nature of the bond. It's giving me, because of those changes, I see, say, the average of that. So a broad signal for alcohols. Also, alcohols, if this is an alcohol, let me see, maybe this is 3000. So, because that will be centered, this is between maybe 3200 and 3500, if this is an alcohol, right? Centimeters -1. But you can also have, in the case of alcohols, a narrow signal, just as this one. But the one that is broad is due to the hydrogen bonding. In case of diluted alcohol, you can also see a sharp signal like that. So when the alcohol is diluted, it's no longer forming hydrogen bonding, and then you will see the sharp signal. Or you may be able to see both. So shape is important. So where is the band? The intensity, so here we see in the carbonyl intense and not as intense, and then shape. Let's look at this applied to this particular spectrum. This is a carboxylic acid, and as we see here, there is a hydrogen bond and hydrogen bond. This is a dimer, so carboxylic acids form dimers. Characteristic of the carboxylic acid, we do have a carbonyl band in 1700, and also we have the OH. In this case, because we have double hydrogen bonding here, this band is so broad that it's actually covering other bands. So likely we have here a lot of signals due to hydrogens attached to carbon sp3, but since the OH is too very wide, it will be on top of many other signals. So but that's essentially that's signature of a carboxylic acid, the presence of the carbonyl band in about 1700 and the OH band.